Welcome to Mrs. Z's Chemistry. In this lesson, we'll discuss the properties and units of length, mass, volume, density, temperature, and time. We'll also discuss something called SI units, the metric system, as well as scientific notation. So you do not always need to write a number in scientific notation. It's best to write the value of your answer in scientific notation if you have a lot of zeros in the number, which means if the number is either really, really small or really, really large. While the number 25.6 could be written as 2.56 times 10 to the 1, this is unnecessary to write it this way. Just record your answer as 25.6. But if your answer would have an exponent of a 3 or 4 or larger, then it's a good idea to write the number in scientific notation. This is so you don't accidentally leave out a zero, and I don't have to waste my time counting a bunch of zeros when I'm grading your answer. We'll talk about how to round your answer to an appropriate amount of digits in a later lesson. So whether you have either a negative 3 or 4 or larger or a positive exponent of 3 or 4 or larger, write it in scientific notation. Otherwise, just keep the number the way it's written. The International System of Units, or SI units, is a set of units that was agreed upon internationally. The SI unit for measuring the length of something is a meter. For mass, it's a kilogram. For time, a second. For temperature is Kelvin. And for the amount of substance, we are going to use the mole, which we'll learn more about in Chapter 3. In this chemistry class, we won't be using electric current or luminous intensity. Those are both physics concepts. This list is actually on the back of your periodic table, right here. Our SI units. You don't even have to remember which units are the SI units. And by the way, we will be using plenty of other units. These aren't the only units we will be using in this class. So while we're here, let's look at the metric system prefixes. These are what we call the base units. They just are written here with dashes, but that means when you have only one of the unit, 1 gram or 1 liter or 1 meter. We call them the base units, and the multiplier is 10 to the 0. If you were to type into your calculator 10 to the 0, that equals 1. The means column, all of these here, is the concept behind the prefix. So a milli is the prefix, and it means a thousandth. There is a thousandth of a meter is 1 milliliter or millimeter. A kilo, up here, the means says 1,000 or 10 to the 3, which is the multiplier, and that means you have 1,000 base units in 1 unit or kilo unit. Notice that the multiplier is for the base unit. And right here, I give you a hint. When you're writing a unit conversion factor, the multiplier, which is this whole column, the number that's in here, that goes with the base unit. And a 1 goes with the prefixed unit, which we'll discuss more in a moment here. You may have been taught in a previous class how to change a unit within the metric system by simply moving the decimal point to the right or to the left. However, I found most students do not do this correctly, and they end up with a very wrong answer. If you move the wrong direction by 3, you'll be in a very wrong answer. So please don't just bump the decimal point over when converting within the metric system. For one thing, we rarely are using just the metric system, and it's often going to be used along with some English unit conversions or other complicated chemistry conversions we'll learn later on. And so you must write out a unit conversion factor using the correct multiplier that was given on that metric system chart. So here's an example. 1 millimeter, the mm is millimeter, the first m is the prefix, the second m means meter. So 1 millimeter is 1,000th of a meter. And we write the unit conversion as the multiplier for milli is 10 to the negative 3. That goes in the base unit because we have 1,000th of a meter is equal to 1 millimeter. In unit conversions, the top must equal the bottom, and the bottom must equal the top. So this is very important. I'm going to say it again. The unit with the prefix, which is the milli, that gets the 1. The multiplier goes with the base unit, which is either just the meter or just the gram or just the liter. So let's look at this one. We have 1 capital M little m is equal to 1 million meters. Notice that whether we write this as a capital or lowercase here and capital here, they mean two very different things. So in chemistry, you need to watch your capital letters and lowercase letters, and your handwriting should distinctly show the difference between capital and lowercase. Otherwise, you could get something very mixed up. The capital M means mega. So we have 1 megameter is equal to 1 million meters. The prefix for mega is 10 to the 6. That goes with the base unit. We have 10 to the 6, which means 1 million meters is equal to 1 megameter. If you were to write it like this and put 10 to the 6 megameters is somehow equal to 1 meter, that would not make sense. 1 megameter is already a million meters. So you're saying you have a million meters, and that's somehow equal to 1 meter? Double check that your unit conversion makes sense. The base unit is not just the bottom unit, that is either the meter, the liter, or the gram, the one that you have only one of. So using that technique I just showed you, pause the video to see if you can correctly convert these units by using the conversion factors. Do not just bump the decimal point over a bunch of digits. So here's the first one. We need to convert 6 megameters into millimeters. So we're going to first write out what we're given. We're given 6 megameters. There's no unit conversion for that. 6 megameters isn't equal to anything in unit conversions. 1 megameter is equal to 1 million meters. The prefix, or the multiplier for mega is 10 to the 6, so that goes with the base unit. The meter is the base unit. And we're going to write the megameter, the 1 megameter on bottom, so that we can cancel the megameters. And now we're going to convert meters to millimeters. The multiplier for milli is 10 to the negative 3. That goes with the base unit, which is the meter. The 1 goes with the millimeter, the one that has the prefixed unit. We write the meter on bottom so that these 2 meters can cancel. So now we multiply across the top and divide across the bottom. And the answer is 6 times 10 to the positive 9. We definitely want to write this in scientific notation because we don't want to count a whole bunch of zeros, 9 of them to be exact, or 9 digits total, and because that would get us potentially mixed up, and maybe we would lose a 0 here and there, and that would give us the wrong answer. So pause and work out the second problem. Convert 3.5 pg to kg. The p in the metric system prefixes is pico, and you can find that on your periodic table. None of this do you have to memorize. So we're looking at a picogram to kilograms. We've got 3.5 picograms, and we need to convert that into kilograms. So notice our multipliers here. 10 to the negative 12, and 10 to the positive 3. Both of these are relating to the base unit. So we're not going to try to add these up because that can get kind of confusing, and it's easy to get that wrong. We're just going to go from from pico to the base unit, and then from base unit to the kilo unit. Start out with the one you're given, 3.5 picograms right here. We have 1 picogram is equal to 10 to the negative 12 grams. Grams is the base unit, so our multiplier goes with the base unit, and the 1 goes with the prefixed unit. We write the picograms on bottom so that we can cancel. Then we have our second unit conversion. 10 to the 3 is the multiplier for kilo, and that goes with the base unit. So 10 to the 3 grams is equal to 1 kilogram. We write the grams on bottom so that the grams cancel. Now we multiply across the top and divide across the bottom, and we get 3.5 times 10 to the negative 15. The SI unit of length is the meter. Yards, centimeters, inches, and feet are just a few other units of length that we'll also be using, and you'll find a bunch of unit conversions on the back of your periodic table. The SI unit of mass is a kilogram. Interestingly enough, a kilogram was originally defined as the mass of a specific object which was kept in a vault in France. However, it was found that this object, which was named Le Grand Decay, was actually very slowly losing tiny amounts of mass over very long periods of time. This standard for the world's kilogram wasn't exactly exact enough, so now the definition of a kilogram is based off of something called Planck's constant, which we'll actually end up using later on this year, and it's tied to complicated physics concepts and quantum theory as well. So our kilogram, or standard for the kilogram, is no longer going to be changing. The SI unit of temperature is the Kelvin. The abbreviation is an uppercase K without a degree symbol, the way Celsius and Fahrenheit have degree symbols. Let's go to the periodic table. On the back of your periodic table, kind of center top here, you'll find the temperature conversion. So let's practice by taking 85 degrees Fahrenheit and converting to Celsius, and then convert that to Kelvin. Notice there isn't a direct conversion going from Fahrenheit to Kelvin. You just go to Celsius first, and then you can get to Kelvin. So using these, we're going to start out by using this one, because we need to plug in our 85 degrees Fahrenheit. 85 degrees Fahrenheit, convert that to Celsius, and then use the second unit conversion here to convert it to Kelvin. Pause to see if you can work this out. So if we have 85 degrees Fahrenheit minus 32, that is in parentheses in our unit conversion here, which means we need to do the subtraction first, then we divide by 1.8, and that gets us 29.4, and the unit is degrees Celsius. Then, to convert to Kelvin, it's actually pretty simple. You just take your Celsius, 29.4, and add 273. And that gets us 302.4. The SI unit for time is seconds. These unit conversions here from seconds to minutes, minutes to hours, and so forth are not on the back of your periodic table, as I assume we all have these memorized since we probably all use them on a daily basis. Volume is the measure of the amount of space occupied by an object. Volume can be measured by cubing a distance unit. In fact, the SI unit for volume is a cubic meter, which is a cube with an edge length of exactly 1 meter. Volume can be measured with cubic centimeters, cubic feet, or cubic inches, or any other cubic distance measurement. Other volume units that are not cubed distance measurements that we'll be using include milliliters, liters, gallons, and quarts, among a few others. A valid measurement must include one estimated digit. When measuring with a ruler or graduated cylinder or any other device that has tick marks, the recorded value must include one estimated digit between the smallest tick mark. So let's look at this graduated cylinder. We can see that the tick marks here are measuring to the 1 whole milliliter. So when we are going to measure where the bottom of the meniscus, remember there's your meniscus, we need to measure to the bottom of it. You can see that the bottom of our meniscus is between the 21 and the 22 lines here. So we know for sure it's going to be 21 something, then you have to estimate, is that closer to 22 or closer to 21? We can say maybe 21.6. On a quiz or a test, I would accept essentially anything between, say, 21.4 to 21.7 or 8 even. However, don't write your answer as a range. Write your answer as one estimated digit, the digit that you estimate it to be. And as long as you're estimating to the correct place value and you're within reason, then you're going to get the correct answer correct. Digital scales and balances, like say a bathroom scale or a kitchen scale or the scales that we have in the chemistry classroom, they already include one estimated digit. There's no way for you to estimate one more digit because there's nothing basing your value off of. So the scale does it for you. So please do not add another digit when you're measuring something, measuring the mass of something on a scale. Let's practice finding the measurements of each of these volumes in milliliters. Pause to work out this first one. All right, so I'm going to explain it. We can see that the tick marks here are from one tick mark to the next is 1 whole milliliter. And we are looking in between this one and this one. Our meniscus is between these two, which is the 25 and the 26. So we know it's going to be less than 26, but greater than 25. We need to estimate one digit more, or one place value more, that is between the tick marks. So you could say 25.1. Since the meniscus is not exactly on the line, I wouldn't say 25.0, but anything between 25.0 to say maybe 25.3 or 4 would be acceptable, as long as you have that tenths of a milliliter digit right there. All right, go ahead and pause the video and work out the remaining 3 right here. The answers are 36 point maybe 6 or 7. And then we have here this middle one. Let's actually look at it a little bit closer. We have 1 whole milliliter between here and here, but then we've got tick marks already showing us to the tenths, which means we need to estimate something in the hundredths place value. So this tick mark is showing 5.4. This tick mark is showing 5.5. The meniscus is somewhere between that. So somewhere between that could be 5.4, maybe 8, 5.45. I would accept anything probably between 5.45 and 5.49. But again, don't write your answer as a range. Write it as the one estimated digit that you estimate it to. As long as you have a hundredths place value for this graduated cylinder, you would get the answer correct, assuming you're within a reasonable range like this. The answer for this last one is 14.8, maybe up to like 14.9. I would probably accept 14.5, even as low as that. Gold in bricks, bars, and coins has been a form of currency for centuries. In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling the centers of hollow gold bricks with lead to fool buyers into thinking that the entire brick is gold. However, this does not work. Lead is a dense substance, but its density is not as great as that of gold, which is 19.3 grams per cubic centimeters. What is the density of lead if a cube of lead has an edge length of 2 centimeters and a mass of 90.7 grams? We are asked to solve for density, so let's find the density equation on the back of your periodic table if you don't already know what it is. Density is in the miscellaneous box here, right here. Density is mass over volume. Units of mass are something like grams or kilograms, even something like pounds, although usually we don't use pounds. And then volume units would be something like milliliters or liters or cubic centimeters, something along those lines. So you're going to have a mass unit of some kind over a volume unit of some kind when you finish this problem. So mass over volume is what we're looking at here. Using this equation, we'll write it out here like this. Density is equal to mass over volume, M meaning mass and V equals volume. See if you can calculate the density of lead here. Pause to work out this problem. The volume of the cube of lead that has an edge length of 2 centimeters is 2 times 2 times 2, which is 8 centimeters, or cubic centimeters. These zeros here are showing the precision of the measurement, and we'll discuss them in more detail later. Density is mass over volume, so notice that neither unit gets canceled, so they are both included in the answer, with the mass unit in the numerator since the mass was in the numerator of the equation, and the volume unit, the cubic centimeters, is in the denominator since the volume measurement was in the denominator of the equation. Density must always have a mass unit over a volume unit as the units.